What causes a supernova? In the vast expanse of the cosmos, where stars burn with an intensity that defies human comprehension, there exists a phenomenon so cataclysmic, so awe-inspiring, that it reshapes the very fabric of the universe. The supernova. These colossal explosions mark the dramatic end of a star's life, releasing energy so immense that it can outshine entire galaxies for a fleeting moment. But what causes a supernova? What cosmic forces converge to unleash such a spectacle? To understand this, we must journey deep into the heart of stars, exploring the intricate dance of matter, gravity, and nuclear forces that culminates in one of nature's most breathtaking displays. Stars, those luminous beacons that punctuate the night sky, are born from vast clouds of gas and dust known as nebulae. Over millions of years, gravity pulls these clouds together, compressing them until the pressure and temperature at their core ignite nuclear fusion. This process, where hydrogen atoms fuse to form helium, releases the energy that powers a star's radiance. For much of a star's life, this fusion acts as a delicate balancing act, with the inward pull of gravity countered by the outward pressure generated by the nuclear reactions within. Yet this equilibrium is not eternal. The path to a supernova begins when this balance falters, driven by the star's mass and its evolutionary trajectory. There are two primary types of supernovae, each with distinct causes rooted in the physics of stellar evolution: core collapse supernovae and thermonuclear supernovae. Core collapse supernovae occur in massive stars, those with masses at least 8 times that of our Sun, while thermonuclear supernovae involve white dwarf stars in binary systems. Both types, though different in their mechanisms, result in explosions that scatter the building blocks of life across the cosmos, forging elements like carbon, oxygen, and iron that form planets, atmospheres, and even the very molecules within us. Let us first explore the core collapse supernova, a fate reserved for the universe's heavyweight champions. These massive stars, born with masses ranging from 8 to over 100 solar masses, live fast and die young. Their lives, spanning mere millions of years, are a frenzy of nuclear fusion. In their cores, hydrogen fuses into helium, and as the hydrogen depletes, the core contracts, increasing in temperature and pressure. This triggers the fusion of helium into heavier elements like carbon and oxygen. For the most massive stars, this process continues, forging neon, magnesium, silicon, and eventually iron. Each stage of fusion releases energy, sustaining the star against gravitational collapse, but each also occurs at an accelerating pace, with the final stages lasting mere days or hours. The critical turning point comes when the star's core becomes dominated by iron. Unlike lighter elements, iron does not release energy when it undergoes fusion. Instead, fusing iron nuclei absorbs energy, robbing the core of the pressure needed to resist gravity. As the core accumulates iron, it grows denser and hotter, reaching temperatures of billions of degrees. At this extreme, the core becomes a battleground of competing forces. Electrons, squeezed to unimaginable densities, combine with protons to form neutrons, releasing neutrinos in the process. These neutrinos, ghostly particles that barely interact with matter, stream out of the core, carrying away energy and further destabilizing it.
What causes a supernova? When the core's mass exceeds the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, it can no longer support itself. Gravity wins, and the core collapses in a fraction of a second, shrinking from the size of Earth to a mere 10 kilometers across. This collapse is catastrophic. The outer layers of the star, no longer supported by the core, plummet inward at speeds approaching a quarter of the speed of light. As the core reaches nuclear densities, the neutrons resist further compression, causing a rebound effect that generates a shock wave. This shock wave, combined with the energy from neutrino interactions, propels the star's outer layers outward in a colossal explosion, the core collapse supernova. The energy released in this explosion is staggering, equivalent to the output of 100 suns over their entire lifetimes compressed into a few seconds. The supernova shines with a luminosity billions of times greater than the sun, visible across vast cosmic distances. The shock wave heats the ejected material to millions of degrees, triggering explosive nucleosynthesis that creates heavy elements like gold, silver, and uranium. These elements, along with the star's outer layers, are hurled into space, enriching the interstellar medium and providing the raw materials for new stars and planets. Yet not all core collapse supernovae are identical. The diversity among massive stars leads to variations in their explosive deaths. Stars between 8 and 20 solar masses typically leave behind a neutron star, a dense, city-sized remnant composed almost entirely of neutrons, with gravity so intense that a teaspoon of its material would weigh as much as a mountain. More massive stars, those exceeding 20 solar masses, may collapse into black holes, their cores compressing beyond the neutron star limit into a singularity where the laws of physics as we know them break down. In some cases, extremely massive stars, those over 100 solar masses, may undergo a pair instability supernova, where the core becomes so hot that photons convert into electron-positron pairs, destabilizing the star and triggering a complete disintegration with no remnant left behind. Now, let us turn to the second type of supernova, the thermonuclear supernova, also known as a type A supernova. Unlike core collapse supernovae, which mark the death of massive stars, thermonuclear supernovae arise from the demise of white dwarfs, the remnants of stars like our Sun. When a star with a mass less than 8 solar masses exhausts its nuclear fuel, it sheds its outer layers, leaving behind a hot, dense core composed primarily of carbon and oxygen. This white dwarf, roughly the size of Earth but with the mass of the Sun, is stable, supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same space. However, stability is not guaranteed if the white dwarf resides in a binary system orbiting a companion star. If the companion is a red giant or another star with an extended atmosphere, the white dwarf can siphon material, primarily hydrogen, onto its surface. This accreted material accumulates, increasing the white dwarf's mass. As the mass approaches the Chandrasekhar limit, the core becomes compressed, raising its temperature. Unlike massive stars where iron marks the end of fusion, the white dwarf's carbon-oxygen core ignites in a runaway fusion reaction. Within seconds, the entire star is consumed in a thermonuclear explosion, obliterating the white dwarf and leaving no remnant behind. The brilliance of a Type A supernova is remarkably consistent, making these events invaluable as standard candles for measuring cosmic distances. Their uniform luminosity, driven by the fixed Chandrasekhar limit, allows astronomers to gauge how far away they are by comparing their observed brightness to their known intrinsic brightness. This property has been instrumental in mapping the expansion of the universe and discovering the mysterious force known as dark energy.
While core collapse and thermonuclear supernovae dominate, other mechanisms can lead to similar explosions. For instance, in rare cases, two white dwarfs in a binary system may merge, their combined mass exceeding the Chandrasekhar limit and triggering a thermonuclear explosion. Additionally, some massive stars may undergo hypernovae, exceptionally energetic core collapse events often associated with gamma-ray bursts, intense beams of gamma rays that are among the most powerful phenomena in the universe. The causes of supernovae are not merely academic curiosities, they are fundamental to the cosmic cycle of creation and destruction. Supernovae are the universe's forges, producing the heavy elements essential for life. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all born in the hearts of stars and scattered by their explosive deaths. Supernovae also shape galaxies, triggering new star formation by compressing interstellar gas with their shockwaves. They are cosmic engines, driving the evolution of the universe itself. Yet many questions remain. The precise mechanisms of core-collapsed supernovae, particularly the role of neutrinos in driving the explosion, are still not fully understood. Advanced simulations and observations, such as those from neutrino detectors and next-generation telescopes, are shedding light on these mysteries. Similarly, the origins of Type Ai supernovae, whether they arise primarily from accretion or mergers, continue to be debated. Each new supernova observed, whether through the light of distant galaxies or the neutrinos streaming from a nearby explosion, brings us closer to unraveling these cosmic enigmas. As we gaze at the night sky, the stars above seem eternal, their light a constant in our fleeting lives. Yet the story of a supernova reminds us that even stars are mortal. Their deaths, in the form of these magnificent explosions, are not an end, but a transformation, seeding the universe with the materials for new worlds and new possibilities. To understand what causes a supernova is to glimpse the heartbeat of the cosmos, a cycle of birth, life, and death that connects us all to the stars.